Hello, in this video, I'm going to show you how to solve a simple problem about binary trees. Here's the problem. Write a method with the following signature that counts the number of nodes with a certain value. So the signature of this method is this. We have public static int, count nodes equal to, that's the name of the method, and it gets a binary tree as an input parameter and a value as another input parameter, and it counts how many nodes is in this tree with the root equal to root, whose values are equal to the given value. So we are going to solve this question using recursion. I already have the code. I'm going to talk about this, and then I'm going to test it using this main method. But before doing that, let me tell you what binary node is. Right now, I'm in the driver package main class, but I have another package called util with a class called binary node in it. If you click on that, you see the code. It's a class called binary node that represents a single node of a binary tree. It has two constructors, two toString methods, height method, a size method, a bunch of traversals like pre-order, post-order, in-order, and then both BFS and DFS traversals. So this is the class. I'm not going to go over all the methods. I only want to focus on what's relevant here, which is the instance fields. We have a binary node of type E, that's generic type, which stores element of type E, a binary node left, which is basically the root of the left subtree, and then a binary node right, which is the root of the right subtree, and that's basically, the two children of a given binary node. These are going to be null if the node is a leaf, but they're not going to be both equal to null if that node has children. And it has two constructors. One is generating a leaf because it's initializes only the element and the rest of the instance fields are null. The other one is going to initialize all the three instance fields, the element, the left, and the right, by setting them equal to three given values, right? So with these two constructors, I can create any binary tree that I want. And in every node, I'm going to store a certain type E, which can become integer, which can be replaced by double, which can be replaced by string or any other type. This E is a generic type, so you can replace it with any type you want. One thing that I wanted to mention before going back to the original question is the toString methods. I have created two toString methods. One of them basically prints the binary tree in a single line by traversing the elements in a pre-order fashion. Pre-order means root, left, right. And the other one is a much longer toString method that uses a queue, and it's much longer, but it basically traverses the nodes in a breadth first search manner or BFS manner, which basically means it traverses the nodes level by level from top to bottom, from left to right, and that way it can print the tree in a much more user-friendly or human-friendly fashion, which I'll show you how it works. Let's go back to the original problem. The goal is to count the nodes equal to a certain value. So similar to many other operations that you need to do on binary trees with recursion, this is another example of using recursion. Why recursion is so useful for binary trees? Because by the definition, binary trees are recursive structures, because the left subtree is a tree by itself, or the right subtree of a binary tree is a binary tree by itself. So they're naturally recursive, right? So when you're solving a problem, your problem can be solved in a recursive fashion, which basically means you solve the problem for left side, you solve the problem for right side, and the aggregation of those solutions can help you solve the problem for the whole binary tree. That's how the general idea of recursion comes into play when you're solving a problem recursively for a binary tree. Let's see this method's implementation. The first thing is the base case. If root is null, return 0. Because if the root is null, that means you have an empty tree, so there's no value to count, so there's no node with the value equal to value. So you return 0, basically. If it's not null, then you need to basically count the nodes with the value equal to value. So we need a counter. Let's initialize it to 0. If the root is equal to value, if root element is equal to value, then increase the counter by 1 because you found a new node with value equal to value. Then call the same method recursively for the left side and call it another time recursively for the right side to count the left subtree and right subtree separately. Count how many nodes are in left subtree with the value equal to value and do it for the right side. And add the counter with the return value of this recursive method when you're calling it for both left and right. And at the end, return the counter. Problem solved. Let's test it. Imagine you have a binary tree like this. The node root is holding a value equal to 1, and it has 2 children. The left child is a subtree like this. The right child is another subtree like this. The left child holds a value 1 in its root, and it has 2 subtrees again. The left subtree of the left child would have 2 in the root and 3 and 1 in the left and right child. The right subtree of the left child has 4 in the root and then 2 and 1 in the 2 and 1 as children. For the right subtree of this whole tree, we have this statement. The root is 6. The left subtree of the original tree is this one, with a 4 in the root and 1 and 2 in the children. And then the right subtree of the original tree is this one, where it holds 1 in the root, 7 and 7 in the both children. Let's print out the tree in 2 ways. One is using the original toString method, which is a prior traversal, and second with a BFS traversal. Let's see. Sorry, I incidentally clicked on debug. Oh, let's do it again. All right. Here it is. The first thing you see is the prior traversal of the tree. And then after that, the toString number 2 will print things in a much easier to read fashion, where you have root on the top, and then the children are 1 and 6. The grandchildren are these, and the grandchildren are these, right? It's a complete binary tree. And we are going to count every single value from 1 to 7 in this tree using this for loop. So we basically count value I in this tree. If I is 1, then the answer should be 1, 2, 3, 4, 5, and 6. Did I miss something? 1, 2, 3, 4, 5, 6. So the number of nodes with value 1 is 6. For value 2 is going to be 3 because you have 3 nodes. 1 is here, 1 here, and 1 here with value 2. For value 3, it's going to be 1 because you only have this one, the leftmost node. Value 4 is 2, 1 here, 1 here. Value 5 is 0. There's no node with value 5. Value 6 is 1. This is the only one, and then value 7 is 2. We have 2 nodes at the lowest level with value equal to 7. So that's how this problem can be solved using recursion. This is the solution.